We're going to walk you through the guided notes on Science Skills and Methods, Part 2. Here we go. This is what it looks like. You're going to fill in all of the information on here where there's blanks. Avogadro's number, as you can see, is already there for you, but we're going to fill this in as we go. So here, scientific notation. Scientific notation is used to express really small or really large numbers easily. Scientists use scientific notation to express large numbers and small numbers in an easier way. So, for example, speed of light, as you can see, is 300 million meters per second. Or Avogadro's number is the number of atoms in 1 mole of a substance. That is a lot of zeros there. So there's got to be a different way. Imagine having to do a calculation where you have to type in all of those numbers several times. That's why we like to shorten it up and use scientific notation as a way to clarify things. So here's another example where there's lots of zeros. Mass of 1 electron. So all those zeros just gets confusing. What if you miss a zero, right? So you want to make it easier on us. This is just too difficult. So all of these examples are in decimal notation, and there are too many zeros to really be useful in calculations. So in scientific notation, numbers are expressed in this form: m times 10 to the nth power, where m equals a number between 1 and 10, and n is a power of 10. So because of this, scientific notation is often called exponential notation. So scientific notation and exponential notation are the same thing, but we usually call it scientific notation in science class. So how to take numbers out of scientific notation? So 10 to the third means 10 times 10 times 10. That's what 10 to the third power means. Or multiply something by 10 3 times. So if we multiplied this, it would equal 1,000. So 10 to the third is equal to 1,000. So 1, there's your period or your decimal point. And we're going to actually move the decimal point. So if we had 1 times 10 to the third, we would start with 1. We'd move that decimal place over to the right. We'd get bigger by 3 zeros. Where are those zeros coming from? Well, 1,000 has 3 zeros in it. So we're going to move that decimal point to the right 3 spaces. So every time we do this, we multiply by 10. So what happens? We move it to the right 1. That's multiplying by 10. Multiply it by another 10. Multiply it by a third 10. And so what I like to say is put eggs in the basket. And so we've moved it there. And so each one of those baskets, you can put an egg in there, or a 0 in this case, and we can see that we're just moving decimal points to solve for 10 to the third. So that's 1,000. So that's how we do that. We just move decimal places. That's the great thing about using the metric system. Multiplying by 10 or 100, it's just moving decimal places, right or left. Well, left if we're dividing, right if we're multiplying. So 10 to the negative third means what? Well, 1 over 10 to the third, okay, that's what that means, so the reciprocal of it. So we know what 10 to the third is 1,000, right? But 10 to the negative third power means this. We have 1 over 10 to the third, which we already know is 10 times 10 times 10. So we're dividing by 10 3 times. It's not a negative number. We're dividing by 10 3 times. So here's our 1. So if it's 1 times 10 to the negative third, we just get to divide by 10 3 times. So we're going to move that decimal place to the left. So dividing by 10 means moving the decimal point to the left. So we're going to do it 3 times. 1, 2, 3. So our decimal place is going to move, and we're going to put eggs in those baskets. Now, we want to, so the decimal place isn't actually showing up, the decimal's not showing up, but it should be 0.001 because we never want to have a decimal point without a 0 in the front to tell us that. Okay, so 0.001 is equal to 1 over 10 to the third. So in other words, 1 over 1,000. So divide 1 by 1,000. So that's what we just did. So a number is written in scientific notation when a number is between 1 and 10, when that number between 1 and 10, is multiplied by a power of 10. For example, if we have 650 million, that can be written in scientific notation as 6.5 times 10 to the 8th power. So let's go through how that is. So here's 650 million meters. So we'll start with that, and the decimal point is always to the right of the number. Even if it's not written, that's where the decimal point is. So we'll put the decimal point there so we can move it. So we need to move the decimal point until you have a number between 1 and 10. So it's on the right side there. Let's go ahead and move it to the left. So to the left, 1, 2, 3, 4, 5, 6, 7, 8 times. So it moves between the 6 and the 5. So 6.5 is a number between 1 and 10. Okay? 8 decimal places. So that's 8 places from the right to the left. So 8 places to the left. Now 6.5 is a number between 1 and 10, like I said. And so you need to multiply that number by a power of 10. So 6.5, the number between 1 and 10, we got to multiply that by 10 to some power. And so what power is that going to be? Well, we figure out the power by how many spaces we moved the decimal point. So we moved this 8 spaces to the left. So as you can remember, we moved 8 spaces to the left. So that is our exponent, is a positive 8. Now why is it positive? We moved to the left. It's positive because it represents a very big number. So it's a much bigger number than 6.5, right? So we're getting bigger by 8 power, by power of 8, I should say. So, and I just explained this. How do you know if it's positive or negative exponent? So if the original number was greater than 1, okay, in this case it's much bigger than 1, your exponent will be positive. Okay, so 650 million meters is equal to 6.5 times 10 to the 8th meters. So as we can see, the one on the right, the scientific notation is much easier to write. As long as we know what it means, we don't have to write all those zeros, and that's why we use it. So this number, 650 million meters, is the same as 6.5 times 10 to the 8th meters. Just one is decimal notation and one is scientific notation. So what if the number is really small? What do we do then? So let's say we have this number. So let's figure out, so this is really small. It's not a negative number because you can't have a negative length here, but it is a small number. It's less than 1. It's not negative, but it's still less than 1. So very, very small meter reading here. So let's take this example. So we start with our original number. And again, we got to remember our rules for scientific notation. We're going to move that decimal until it gets to be between a number between 1 and 10. Okay, so here's the decimal point. So let's move it until it's between a number between 1 and 10. Here we go. To the right. 1, 2, 3, 4, 5, 6, 7, 8 spaces to the right will give us, again, 6.5. So again, let's go back real quick. Oh, I guess I can't go back here while I'm recording. But 6.5 is a number between 1 and 10. All right, so there we go. We did the first step. Now we need to multiply that 6.5 times 10 to some power. So what power are we going to use? Well, again, it's the same thing. All right, we're going to figure out that we moved 8 spaces to the right. Okay, so remember that. We moved 8 spaces to the right. So that's going to be our exponent. So we're going to put an 8 there. So 6.5 times 10 to the 8th. But it's not 650 million like it was before. It represents a very small number. So it's a very small number. It's less than 1. So our exponent is going to be negative. So we have to put a negative 8. So here we go. We got 0.000000 0.065 meters, which is hard to say or whatever. We can actually say that decimal is the same, decimal notation is the same written in scientific notation. So 6.5 times 10 to the negative 8 meters. These two are the same. They're the same number, one in decimal form, one in scientific notation. So we've just done two examples of how to turn a decimal number into a scientific notation number. Okay, so let's move forward and try something else. What if the number was already in scientific notation and I want to put it into decimal notation? So let's say our example is 7.24 times 10 to the 4th meters. Let's turn that into decimal notation. So it's a positive exponent, so that matters. We got to pay attention to that. So here's our example. 7.24 times 10 to the 4th meters. So 7.24 times 10 to the 4th, we rewrote the original here. Here's our decimal point, all right? And so the exponent is a positive 4, so that tells us which way to move the decimal point. So we're going to get it to be representing a big number because it's a positive 4. All right, since the exponent is positive, we move that decimal point to the right 4 places. So let's do this. 1, 2, 3, 4 spaces. All right, putting the zeros in the missing places, I call it putting the eggs in the basket. We're going to add those 2 zeros. Okay, and that's what I just said. I call it putting eggs in the basket. So there's our new number. Our new decimal point is on the right side of that, and we always want to add, commas to show this. So we actually go from the right. We're going to count 3 spaces back, and that's where we put our comma. Okay, so 72,400. That is our answer. Okay, so 7.24 times 10 to the 4th meters, that number, is equal to 72,400 meters. So we've taken a scientific notation number and turned it into a decimal notation. So there you go. So what if the number was already in scientific notation and you want to put it in decimal notation? All right, so again, let's 7.24 times 10 to the negative 4th. So it's the same type of question, but now it's a negative exponent. So let's look at that. So let's rewrite this. 7.24 times 10 to the negative 4th meters. If we rewrite that, again, whether it's positive or negative does matter. So the exponent is a negative 4 in this case. And so since it's negative, we're going to take that decimal point and we're going to move it to the left 4 places. So to the left, let's do this. 1, 2, 3, 4. So once we do that, we can put the eggs in the basket, right? 1, 2, 3. But we also want to put our decimal there and a 0 in front of it, because you don't want to just have a decimal without a 0 in front. It could look like just a smudge on the page. So we want to make sure we understand that there's a 0 in front of this. So we're going to put that there. So now, if we rewrite it, this is 7.24 times 10 to the negative 4th meters written in decimal notation. So there we go. We have that number, scientific notation, and now we have it in decimal notation. Same thing, they're equal to one another. Now let's go on to types of graphs. So types of graphs, we can see a line graph in the upper left-hand corner. So it shows us that there's tree growth from 2003 to 2007. It's a line that's connected, so we see it change over time. We also see in the upper right there's bar graphs that compare things. So in this case, this is July and August sales. So we can see in week 1, August was represented in red, blue is July, and we can see the changes each month and compare each month, or compare the weeks of those months, I should say. Then we have the lower left, we have the pie chart, which just kind of breaks it into 100%, right? Each one of those slivers or slices of pie will, added all up, will be 100%. And then we've done something we've already learned about, is a scatter plot graph. So let's look into these. So line graphs are used to track changes over short and long periods of time. When smaller changes exist, line graphs are better than bar graphs. So if it's a small change, line graphs are going to show it easier for us, for our eyes to be able to make sense of it. So line graphs can also be used to compare changes over the same period of time for more than one group. So you can have more than one line is what we're saying. Bar graphs are used to compare things between different groups or to track changes over time. However, when trying to measure changes over time, bar graphs are best when changes are larger so we can see it. So if you look at this sales, they're a drastic difference between the weeks, right? So we can see the difference in the change in the red and the blue and compare them to one another, and we see them. If they were very slight differences, they might be a little bit more difficult. But since these are big changes, we can see them with a bar graph. Pie charts are generally used to show percentage or proportional data, and usually the percentage represented by each category is provided next to the corresponding slice of pie. So pie charts are good for displaying data for around 6 categories or fewer. If you have too many things, it gets kind of hard to read them. So this is an example of NBA championships, and we can see that a few teams have won the majority of the NBA championships over the years. So we can see Boston Celtics at 24%, the Los Angeles/Minneapolis Lakers, 22%. We have the Philadelphia 76ers, San Francisco and Golden State Warriors all have 8%, Chicago Bulls 8%, San Antonio Spurs 7%, and then all the other teams are 31%. So there we go. That's a pie chart. And then scatterplots, we've already done our scatterplot here, so we've already kind of figured this out a little bit. But a scatterplot, or sometimes as Excel calls it, a chart, we can call it a scatter chart, works best when comparing large numbers of data points without regard to time. So if it's over time, sometimes we like to use line graphs, right? But scatterplots kind of show us a number and a mix of data points. So they're scattered around there. So this is a very powerful type of chart and good when you're trying to show a relationship between two variables, the x-axis and y-axis. Obviously, this is an example up here, so it doesn't have its axes labeled. Obviously, we should understand scatterplots a little bit more since we've talked about that. Now, correlation, so relation. What comes to mind here is relationship. So the relationship between two variables is called their correlation. So scatterplots usually consist of a large body of data. The closer the data points come when plotted to make a straight line, the higher the correlation between the two variables, or the stronger the relationship. So let's look at some examples. On the left, we have a perfect positive correlation. It's perfectly positive because it's in a straight line, so that's what makes it perfect. It's positive because the line is actually going upwards from left to right. The middle picture shows a perfect negative correlation, which is, again, it's perfect because it's a straight line. It's negative correlation because it's a downward slope. And then the one on the right is no correlation. This is just scattered data. It's not forming any sort of pattern. We can't see any lines or anything being made. So we would say that these two variables are not correlated, or they don't have a relationship. So a high positive correlation, again, this is a very tightly bound, it looks kind of like it could be a line, a straight line, so it's a high positive correlation. If we did a best fit line here, it would show an upward slope. The second one is a high negative correlation. Because it's close together, it forms kind of a line. We say it's high correlation, but it's negative because if we did a best fit line, it would show a negative slope. The third one is a low positive correlation. So it's still a positive correlation. It can still kind of make a line, but it's a fatter line, so it's not as close to a straight line, so it's a low correlation. You can see that it's positive because a best fit line would show us that it's actually increasing, right? It's an upward slope. And the last one on the right, the low negative correlation, it's wider, it's not a full straight line. So it's a low correlation, and it's negative because the best fit line would show us that it's a negative slope, heading downward. So that's correlation. And then we'll talk about proportionality. So there's direct proportionality. So if something is directly proportional. So this means as the independent variable, your x-axis, as those values increase, the dependent variable increases as well. And if it's a straight line, this is going to be directly proportional. So we can see that that's what directly proportional means. We'll get a straight line on a graph. going upwards, an upward slope. If we have inversely proportional, the inverse here, this means that as something is decreasing, so in this case, the independent variable, as those values go from left to right, they're increasing, right? But the dependent variable, the y values, are decreasing in that same thing, and we get this kind of slope downward, kind of a curve, as we can see. So this is a graph that represents something that is inversely proportional. So a way to remember that, if one goes up and one goes up, it's directly proportional. If one goes down and one goes up, it's indirectly proportional. Inversely, I should say, inversely proportional.